This is without a doubt the best quantum physics video that I've ever seen. And the reason it's the best is because it was able to change my mind. And unfortunately, it's pretty rare for people to change their minds about anything these days. But this video actually changed my perspective about wave function collapse and the observer effect. So a little bit about my background. I'm not a scientist myself. I'm just someone who's very interested in science. I assume that's the same for most of you. And this video was the most valuable thing that I've seen on the topic, and I figured it could be of similar value to you, so I wanted to share it. And I've seen quite a few different videos about quantum mechanics and read books. Another interesting one is from Sabine Hossenfelder, The Bomb Experiment. That's also a pretty interesting one. But this is the only one I actually changed my mind about some of the fundamental parts of quantum mechanics. And I'll jump in quickly, but I just want to share my previous perspective on quantum mechanics, so you could then juxtapose that against my latest opinion on it based on this video. So before this video, I kind of had my view was mostly similar to Einstein's, where it was kind of critical of quantum mechanics, saying that, okay, even though the experimental predictions are pretty accurate, there's still probably something that we're missing. In particular, God doesn't play dice, right? I didn't like that the statistics, that the probability would be so fundamental to how quantum mechanics work. I'll give you an example. And my background with statistics is actually decent. My background is in finance, so I've taken quite a few statistics courses and probability and whatnot. Just because you can describe something accurately with probability doesn't mean that it's actually random, right? So for instance, let's say I'm rolling a dice, a 6-sided dice, right? I can predict pretty accurately it'll land on the number 3 16% of the time, right? And if you roll it a million times, then the numbers will be pretty close to that. It'll be pretty accurate, but that doesn't mean that it's actually random what side the dice lands on, right? It's based on how you threw it. If you threw it the exact same way at the exact same starting position, the exact same velocity, you're hitting something with the exact same hardness, right? If you throw it the exact same way every time, it will land on the exact same thing, exact same number every time. So it's not actually random. It's not actually random, even though it can be described randomly when you run the numbers a bunch of times. And that's kind of what I thought about quantum mechanics. I didn't think it was actually random. It was actually, in, maybe a superposition state where it's doing everything. Even though we can calculate it accurately, I figured that there must be something we're missing. And that was my initial perspective coming into it. But I'll let you, we'll go ahead and move forward. And the title of this video is the quantum eraser experiment. I'm not going to go into detail on what the quantum eraser is. You can look that up on your own. It's basically a way of trying to erase the information, the which way information, and see what happens. But again, I won't go further into that. Let's go ahead and dive into the video. It's already going to be a long one at 20 minutes. Of the video itself, so I'll try not to make this too much more than that with my commentary. I just wanted to let you know how valuable this was to me and kind of my initial perspective, my initial skepticism of some of the probability related things related to quantum mechanics going into it. So let's go ahead and start.
In quantum mechanics, things behave differently the moment they know you're watching. I'm going to do an experiment where light changes from this to this, all because it was being observed. But why do quantum objects care if they're being watched? This is the mystery that got me obsessed with quantum mechanics years ago. But I love this experiment because the 3 variations of it explain 3 crucial facts about measurements. And the third might even be a solution to the measurement problem itself.
Yeah, I just want to say that the observer effect is probably one of the most misunderstood parts of quantum mechanics. And I believe this even before this video, or a lot of people, they thought it was just like, I think it was from a friend of mine that quoted something from Neil deGrasse Tyson where he said, oh, okay, it's just that you interacted with it. And when you bumped into it, you changed it, right? Almost as if it was like a ball was on a table. And then when you poked it, it went the direction you poked it, and it's as simple as that. There's some truth that it is the interaction and not the consciousness of the observer. I think that part is true. It's not that you need to be, over a certain IQ and conscious to collapse a wave function. It's not that. So I think that distinction where they're trying to say, hey, it's not just about consciousness. It's not like some magic about your mind. You're not casting spells in quantum mechanics, right? When they make that clarification, it starts to make some people get the mistaken takeaway that, oh, okay, well, if it's not pure magic based on your mind, well, then it's just completely normal. We just bumped into it like a regular ball, but it's not like that either. It's more mysterious than you think, but it's not mental magic either. It's not mental magic either.
In the double slit experiment, you shine light on two very narrow slits, which I've represented here like this. And you can see that the light sort of spreads out and it goes through both slits. In fact, we know that this is what happens even with the laser because you can actually see it.
And you can clearly see those two lasers here. And this is one of the reasons this video is my favorite, is because it's not a, abstract, let me tell you a bunch of rules and hope you understand it. You can visually see everything that she's going to show you with your eyes, with these lasers in the smoke. You can see everything. So it's not abstract. It's not a diagram of what happens hypothetically in some, incredibly small quantum experiment. This is everything she's going to do is in your face like this, and you can see it clearly with your own eyes. You can see the quantum physics happening, which is why this is such a powerful video.
If light is somehow wave-like, then this kind of makes sense, because it's like saying the wave will spread out and then it will go through both of these slits and make new little waves. Eventually, these two little waves will spread and overlap. And as you can imagine, when two waves get in each other's way, they interfere with each other. And this is what causes the classic double slit pattern. This is a double slit, which hopefully you can see. And now I'm going to put the double slit in front of the laser and turn off the lights. Let's see what happens. And this is what the pattern looks like. And just as a side note, I never get over how beautiful this looks. Just crazy. And so now you get this double slit interference pattern, which looks like a whole bunch of little dots, right? Like there are these sort of bigger regions, and then in each of those regions, there's like little sub-regions as well. That's the double slit pattern. This all makes sense if you buy into the classical wave theory of light. But this isn't classical mechanics. This is quantum mechanics. And so many of my comments were like, shouldn't this be impossible? How can it be possible to see light going through both slits at the same time? And I understand why people are confused, because this seems to contradict one of the big ideas that I want to talk about in this video, which is that measurements cause collapse of the quantum state. So here's what that means. Light like this can be in a quantum superposition of doing multiple things at the same time. So for example, this light is in a superposition of going through the left slit and the right slit. And you can see why that's totally fine. It'll just lead to this overlap. But this rule says that this is fine as long as we don't ever try and find out whether the light went through the left or the right, because when we do, we cause it to collapse. So for example, if I was somehow to measure what the quantum state was doing by, let's say...
One thing I want to point out here, and this goes to kind of the point about the theory that my friend has, which is, if you bump into it, then clearly, you caused it to behave differently, right? She put the observation on the other side of the slit, right? So like for the most part, people will think that, or at least some people that had this misunderstanding will think that, oh, well, if you measure it here, then you just like bumped into it and you caused it to go through the left one or the right one. But you can even measure it later after the fact, after it's already gone through whatever slit it went through. If you measure it even later, it'll collapse, right? So it's not like you have to have measured it before it went through the slit. You can measure it after it's gone through the slit and still cause it to collapse. Just want to call that out.
Looking at the light and seeing it going through the left slit, then I would collapse the state. And so it would have to only do one of these things. And let's say the right one might disappear. And so the rule says when you look to see whether the light went left or right, then you collapse it to just going through one of the slits. So shouldn't that have happened when we were doing our experiment and looking at the way light was going? Well, don't worry, it's not actually a contradiction because of this. Suppose this is all the light coming out of each of these two slits before we measure it. And then we use the same technique that I did.
So I just want to just clarify in case it's unclear. Right now, she's trying to explain why we were able to see the double slit pattern, because they're like, okay, if you can see it, then shouldn't it have collapsed to being a single slit? She's going to explain why it hasn't collapsed to being a single slit and why we can actually see the double slit pattern. Because some people's intuition would say, well, if I can see, the double slit pattern, then shouldn't it have collapsed into a single slit pattern? They think you should never be able to see the double slit.
See the light, which is to use a horrible carcinogenic smoke machine to make these little droplets of smoke here and there. And what this will do is when a bit of light hits one of these smoke particles, it will get deflected. And now that bit of light will no longer go through, but the rest of the light will go on sort of unaffected. So some little bits of light will deflect off these smoke particles and might even end up in the observer's eye or in the camera lens. And so that's why we can kind of overall see the path of this light. But it doesn't count as a measurement of most of the light, because you can see that most of the light goes completely unmeasured by the smoke particles because they never encounter any. And so that's why the smoke is actually not a good measurement of which way the light goes. But there has to be a cleverer way of figuring out whether the light went left or right and collapsing the state. And in fact, there is. Here's how we're going to do it. So when we imagine light as a wave, we're usually thinking of the wave sort of waving up and down, right? Like these are all the peaks of the wave and they're sort of up and down. But actually, light can be a mixture of all kinds of directions of these waves. Like they could be waving left to right. They could be waving like this or like this. And this light is just going to be a huge jumble of all kinds of different directions. But what if we used this stuff to filter out the light? So let's say that we have some light coming in some random direction here, but we only let through light that is oriented up and down, like this. So only this light would be able to go through. Or what if we turn the filter around and now it only would allow light going this way? So this light would go through, but nothing else. Well, we could do that and it wouldn't really do much for us. But here's the really clever bit. Why don't we do both? Why don't we put a filter in this direction over just the left slit and a filter in this direction just over the right slit? That means that light that makes it through the left slit has to be oriented like this, vertically. And light that makes it through the right slit has to be oriented like this, which is horizontal. What we've just done is we've marked these two slits. The light coming out of them are very different. And so if we want to know whether a bit of light is coming from the left slit or from the right slit, all we have to do is put a filter like this. Because a filter like this will only allow through vertical light, and it won't allow through this horizontal light. And so by measuring this polarization, we've also measured which direction the light went through, and we've collapsed it to only going through one, which is the left slit.
So I just want to clarify here, right? So if you only had one filter, let's say a horizontal filter that went over both slits, then it doesn't collapse anything because you still don't know which slit it went through. Right now, when you mark it, by having one, a vertical one on the left slit and a horizontal one, say on the right slit, now that light that goes through, right? There's now information about which slit that the light went through. And then she says you placed a second filter that she has in her hand, the second vertical filter. And basically on the other side of that vertical filter, the light from the horizontal side, the light from the horizontal side is not going to make it through that vertical filter. Only the light from the left slit or the top slit, based on how you're looking at it right here, will make it through both vertical filters. So you'll know that everything on the other side of that filter came from the left slit, if that makes sense.
If our rule that measuring the quantum state really causes it to collapse is true, then we should see that the light goes from being a...
And there's a piece that some of you who are more observant may be predicting about what some parts of this experiment that may be unnecessary, but we'll get there soon. So if you have noticed that, then you're paying good attention and you have a good quantum mind that's focusing right now.
Double slit pattern to a single slit pattern. So if we can put these filters behind the two slits, then we'll have a way to test whether measurement collapse really happens. It was very, very finicky, but I finally got it to work. Here are the little filters that go behind the slits. So let's see if this really causes measurement collapse. This is the new pattern, and you can see that it actually looks quite different. Like, the big patches are still basically where they were, but now there isn't these little lines in them. And just to see how different this actually...
so it's smooth here. So you may think that, that this looks like the double slit because there's these gaps. But in reality, at least in this experiment, when you run it, there's going to be those gaps, whether it's a single slit or a double slit. The difference is the double slit has those little small gaps. If you remember from the beginning, if you don't, just rewind the video. The double slit will have those small interference patterns within those larger slits, where the single slit pattern is just those big, smooth things that you're seeing on the screen right now.
Let's turn the camera around. You can see that there's basically only one beam that's really visible, which is the middle beam. The tiny little beams that you see in the double slit pattern are mostly gone. So observing this light really did change it. Just to double check that we really have collapsed this light into just going through one slit, I compared this pattern to what would happen if you did just have one slit to start off with. And you can see that they look very, very similar. The spacing of these bright bands is pretty much identical, which proves our hypothesis that observing the light really collapses it. But here's the really trippy bit. So this filter here is what allowed us to know that the light is going through the left slit. But what about if I just remove it? Here's what the light looks like with the filter, and here's what it looks like without. It's basically the same.
Right, so this is that foreshadowing I was talking about earlier, the part of the experiment that was unnecessary. The which way marker, when you measured the polarity left versus right, even if you don't know which one, the fact that you could know which one makes it already collapse, right? This second filter just tells us that it went through the left one, like that all the light on the other side of the filter went through the left one. That's how we know which one it is. But even if we don't know it, as long as it's knowable, as long as it's possible to be known, right? Once it's marked, it's possible to be known, then the collapse already happened. So it doesn't matter whether or not you know it. It matters whether or not has been measured, whether it's been marked, whether it's been possible, whether the information has leaked into the environment. Even if you don't know what it is, if the information is there, then it's collapsed.
It just looks a bit brighter without. So what on earth is going on? This second version of this experiment leads us to our second big idea for this video, and it's that measurement doesn't need a conscious observer. Measurement happens when information is leaked to the environment. To understand why this is true, let's look at our experiment again. So remember, we said that this bit marks which way. What I mean by marked is the information about whether the light went left or right has now been transferred or copied onto something else. And in this case, it's the polarization of the light. So now the polarization of the light contains that information about which way the light went. And then that other filter we had, this was technically the measurement. When this is here, we know that the light that comes out must have gone through the left slit. And so we expect to see the single slit interference pattern, not the double slit one. So it'll look something like that, whereas the double slit one would look like this. Now, the remarkable thing that we found was that we didn't actually need this measurement. Even without it, we still only get the single slit interference pattern and not the double slit one. And it's because marking which way the light went is as bad as a measurement. One way to think about this is that information got leaked from the particle's position, so where it was, to its polarization. And this is a more general phenomena in quantum mechanics. Let's say we have an object that's in a quantum superposition of doing two different things, like our light, which was in a superposition of left and right. Then, let's say another particle comes along and marks the two options. For example, if the original particle was in state 1, the new one will lose energy. But if the original particle was in state 2, the new particle will gain some energy. So the energy of this new particle now carries information about the original particle. And so that's what I mean by marking. Now let's say that that new particle just flies off with that information. What happens to our original object? It will look like it collapsed to doing one of those two things. The information leaking into the environment will look just like a measurement. This is called decoherence. Okay, but our story's not over yet because I want to show you the craziest variation on this experiment yet. So far, we said that having these filters.
I just want to call out that decoherence, I think, is the better way of thinking about collapse than like observer. I think observer adds a lot of unnecessary connotation around it. You think about eyes, you think about mental states and all of that. Where decoherence is more about and you can look up maybe a better definition than what I'm going to give you off the top of my head here. But decoherence is more about the quantum state becoming out of a simple alignment where everything is in a smooth superposition. When it starts to interact with other things in a way where things start to get messy, then your clean superposition state collapses. And I think that's one of the reasons it's hard to scale up quantum computers, because the more you add to it, the higher risk of decoherence, and then you lose all the cool quantum stuff. But I'll go ahead and let her continue here because we're starting to get to the good part.
On top of the double slit marks which way the light goes, and since that information has leaked into the environment, it collapses the light to either going through the left slit or the right slit. But if that's true, then how do you explain this? Here we got the single slit pattern that we've gotten used to, but I can actually recover the double slit pattern by putting a filter in front of this, but not in the direction that we were doing before. If I put it at this 45-degree angle, you can see that I actually recover the double slit pattern. I just think this is insane. How crazy is that?
Look at that. She's basically uncollapsing the function, right? Like that's how it looks, right? So again, but before you have the different polarity filters on the other side, what's happening is the light is going through both slits and interfering with itself. And that's why you end up with those little dots, all those little, where the peaks hit the peaks, it amplifies, where the peaks hit the troughs, they cancel each other out. You end up with that interference pattern on the wall when you don't know which ones it went through. Once you mark the different polarities, one polarity on the left slit, one polarity on the right slit, it's no longer going through both because we know which one it went through. Okay, so then you get the single slit pattern again. Then when you put this filter at the 45-degree angle, you get the interference again, right? And this is what really blew my mind, because it's like, if you think of collapse as like a one-time thing, like, okay, well now it's behaving like this, right? Now it's behaving as if it went through just one slit. That's okay. But when you can get it back to have gone through both like this, then that means that the collapse basically never happened. That it always still went through both. We just only saw one version of it, which is crazy. And that's what leads to the many worlds, the multiverse, which again, stuff I never really liked about quantum mechanics. I never liked the many worlds theory. It seemed like too big of a stretch for some stuff that we were unsure about. But the fact that she can just uncollapse it so that she can basically get the interference again, even though we only saw it going through one slit, she can make it with this second filter such that everything after that filter has gone through both slit, but between the light, between the first filter and the second filter, it still only went through one. That's crazy. This is crazy to me. I'll let her go forward, but this is what really blew my mind.
See the double slit pattern just pop back out. It's even crazier when you look at it this direction, where this is the single slit pattern, which we expect because of our observation. And here is the filter. And look, it brings back the double slit pattern. The double slit only exists in front of the filter.
Right, that's important. It only exists in front. So between the filter and the initial, because there's two filters, right? Between filter 1 and filter 2, it's a single slit pattern. On the other side of the second filter is double slit. That's crazy.
But behind it, like, you can just see the single slit pattern. This is such a bizarre experiment. Yeah, look at that. How is it possible that if this is a measurement that collapses the light to only going one direction, that we're able to make it go through both directions later on by putting a filter in like this? Like, we're influencing whether the light went through both of the slits here by putting a filter in here. That's where the third and I think most interesting lesson from this experiment comes in. Measurement collapse is an illusion, at least sometimes, and maybe always.
This is the craziest part. This here, because I can't argue with it. I just saw it with my own eyes. I saw that it appeared to have collapsed, but the information is still there as if it went through both ways, because it will interfere with itself again on the other side of the far filter. That's crazy to me. That's crazy. And I can't argue with it because I just saw it with my own eyes. Right. So it basically means that superposition state, even though it appears to have collapsed, it still went through both and it's still theoretically recoverable. That's crazy.
So in the case of this experiment that we just did, which is called the quantum eraser, measurement collapse was an illusion. So here's what I mean. Originally, we said that just marking which way this light goes was enough to cause it to collapse. Let's say that it has in fact collapsed to just going left. Then it goes through some other filter, and then we end up with the double slit pattern. How is that possible if the light really had only gone through one of them? That would be like saying suddenly, after going through this other filter, not only does this light continue, but suddenly there's new light coming from the right slit, which is impossible if there wasn't any here. So we must have been wrong. There must have been some light still coming from the right slit at this point. But then how come without this filter, we didn't get a double slit pattern? We only got a single slit pattern. Well, what this shows is that without this other filter here, what happened on this side is just fake collapse. Or if you want to be technical about it, it's called subjective collapse. This sounds really bizarre, but it's actually not controversial at all. So what happens is when you mark which way the light goes, it doesn't actually collapse. Both bits of light are still there. They'll overlap in space, but even though this is happening, they're no longer able to affect each other. And remember, it was this interference that caused the double slit pattern. And now that that interference can't happen anymore, you just get the single slit interference pattern. Like I said, I know this sounds weird and it sounds a little bit mystical when I have to say it in English like this. But when you write down the mathematics of it, you kind of see why they're no longer allowed to interact. And it's all because of the fact that they're marked. Each one is marked in a separate way. And those two bits of light, now that they have this difference, aren't able to interact anymore. If you're interested in actually seeing that maths for yourself, then I've actually written it up.
So I won't comment on the math. I believe some people have, one of the comments I saw was that, if you mark the polarity, right? If the polarity is vertical for one and horizontal for the other, well, then it will make sense that those polarities wouldn't match in terms of being able to create constructive or destructive interference based on the peak trough. So I want to call that out. I don't think that that's applicable. I think that's a good intuition. That's the good thing to call out, but I don't think that's what's explaining the difference. I think it's a matter of the decoherence and the fact that it still went through both. We just don't see it, and you can still recover it by the 45 degree. Because even that argument, right? How would a 45 degree angle recreate? If you are concerned about the polarity, waving up versus waving left and right, then a 45 degree one wouldn't fix that either, right? But it clearly does. See, I can understand that being an idea that someone has, is that, okay, but the nature of this experiment was polarity based and different polarities can't interfere that way. But that's not true. Like I said, because the 45 degree angle wouldn't fix that. And even if you didn't have, filters, the light's by default a bunch of different polarities anyway, right? It's a jumble of waves in different directions. So I don't think that's, a good answer. Again, if someone knows better than me, feel free to argue about that and put your information there. But I'm gonna go ahead and close the video here. So I don't think there's a whole lot new. It's just the main thing to me is that she was able to basically uncollapse the wave function, right? And if you can uncollapse it and get interference later after it already appears to have collapsed, then that means it was always still there. Which is crazy. I'll let her go a little more, and then I'll close the video.
And the link will be in the description. But if you're happy to accept that, then you'll understand why the 45 degree filter fixes everything. Remember, light that's coming through the left slit is vertical, and light that's coming through the right slit is horizontal. But if I put a 45 degree filter in between, what happens is that this light has a 50% chance of going through, and this light also has a 50% chance of going through. So after this 45 degree filter, firstly, both bits of light will now be oriented 45 degrees. So they'll both be oriented kind of like this. And any light that's gotten through this filter is equally likely to have come from the left or from the right now, because both of them will have been polarized in the 45 degree direction. And so, in a way, this filter undoes what this one did. It unmarks them. In other words, this filter has erased the information about
and this is the quantum eraser part. We knew which way here, right? We had information, decoherence. After this, we lose information. It's back in coherence again, and now you get interference. But again, to understand this, you have to know that even though it looked like it only went here, to us, it was still going through the other one, right? And we know that because it can interfere on the other side after it's unmarked, right? So like, even though this comes here and it gets oriented on the 45 degree angle, and we let's say we know it didn't go through here, all of a sudden this starts going through here again, from our perspective, which is, again, that subjective collapse thing, which is still pretty wild.
Direction the light went. You can't just look at the polarization anymore to tell, did it go left or did it go right? And so everything is back to how it was. And you end up with the double slit pattern again. I love this experiment because it's a really tangible example of a more general thing in quantum mechanics. So you can have a particle that is in a superposition and then interacts with some other particle in a way that seems to make it collapse. And we might say that the second particle measured the first one. But then if you're able to get that second particle back and erase the information that was on it, you see that the first particle was still in a superposition, and now it acts like it was in a superposition the whole time. What I really like about that is that this is potentially a general story about what measurement really is in quantum mechanics. So replace that second particle with a measuring device or a human, whatever you want. And what we see is we have a quantum object, and when the person or the machine measures that object, it seems to cause that object to collapse. But it actually is recoverable. If there was a way to remove all of the information about what that particle was doing from your machine or from, your brain, the entire environment, every photon that interacted with that particle, then you're able to see that the particle was never actually collapsed at all. This whole thing of sort of fake collapse is called decoherence. And like I said, it's not controversial that decoherence happens sometimes. Like this example is a really great one of decoherence happening and then getting erased. So it's not controversial that this can happen. What is controversial is this the answer to the measurement problem? When we talk about measurement, is this what's always happening? It's so controversial because once you start saying that this is the solution to the measurement problem, what you mean is that every time you go and measure a quantum particle, there are two versions of you, one that sees the particle do one thing and the other that sees the particle do the other thing, and both still exist. You will feel like you have collapsed to one of those and the particle has collapsed to one of those. And every experiment that you try to do to get evidence about whether the particle has collapsed to going just one way or if it's still going both ways will show you, no, it's definitely collapsed. You'll only see the single slit interference pattern. But if you were able to somehow undo all of that, then you would see that actually there was no collapse at all. And really what happened...
So this is how you end up with the many worlds, right? Because every little quantum observation, decoherence, would have its own set of superpositions that could now have been collapsed into one thing. And, at that point, it doesn't take long for you to end up with an infinite number of simultaneous possibilities. I think what we know for sure is that there's clearly a superposition state where it interacts and creates something like that interference pattern. We know that happens. And we know there's also a state where where it's not a superposition, where it only does one thing, right? We know there's those two different states for sure. Now, we don't know which version we're going to be in when we measure it. And I think that's where the probability comes in, right? You basically say, okay, well, given all of the possible quantum states that there could be, which universe would be the most likely one for us to end up in? And you can do those statistics, and those experimental results have been very highly accurate from a scientific statistical perspective. So we know that there's a superposition state that behaves one way. We know that there's a collapse state. And based on this experiment, it looks like even in a collapse state, you can still recover the superposition state later, which makes it seem like the superposition state is the more fundamental reality, which is pretty tough to grapple with if you don't want to believe that, which I don't want to. But how can you argue with reality?
Was that you and the particle were in superposition, which I think is a very uncomfortable thought. This solution to the measurement problem is called the many worlds interpretation of quantum mechanics. And I think that at least mathematically, it's extremely nice. Because think about it, the maths going on here, we already know that it can happen, and it does happen in quantum mechanics. So you don't need to propose any new mechanism to explain measurement, unlike the traditional interpretations of quantum mechanics that do make measurement this special and very weird thing. In many worlds, it's completely natural. This is exactly what you would expect to happen if you take quantum mechanics very seriously. But I think that it does take a while to let that maths really sink in.
Right. It's easy to do math, depending on who you are. I don't want to generalize that, but it's easy to do math and come out with an answer. I remember, I think Richard Feynman was given a lecture, and he talked about how some students could do the math, but they wouldn't understand the real world implications of their math. Like they wouldn't be able to look at, you'd say light behaving a certain way when it's like, I think it was like interacting with like a sheet of oil on top of a water surface, and like how it makes that like rainbowy type look. Like they may be able to do the math for it, but they may not even understand well, how the math applies to what they're seeing basically. So trying to bring that into reality, and then accept it. And in this case with quantum mechanics, trying to accept that reality that, we don't need a special rule for measurement, that it's just the base nature of reality is just jumble of superpositions of probabilistic quantum events that were all duplicated in all of the states simultaneously, only experiencing our own universe through decoherence. But if we could theoretically go back and remove the decoherence, we'd see the fundamental truth that everything is just a big soup of superpositions and probabilities. It doesn't feel good. It feels kind of magical. It feels like a stretch, but it's hard to argue it when you see the experimental results. So I'm gonna go ahead and close the video here. Thanks for your time. Hopefully this was as helpful and interesting for you as it was for me. If you have ways of fighting it, of explaining that it's actually something simpler than it is, I welcome you to try. But I do think that this, at least to me, it makes sense, even though I don't like it, that it's even when it appears to have collapsed, it's still going through both. So if you could persuade me otherwise, I'd appreciate that, because that's what I'd rather believe. But sometimes you can't believe what you want. You have to believe what's true. And that's, to me, an indicator of an intelligent person. So, but yeah, I'm totally welcome to being persuaded to my original position. But I had to change my mind after this video. So thanks everybody. Have a good one.